This is John Black, super chemist. Before I go into how to make benzyl chloride, I want to go over these three real quick. These three reactions because they're so similar that it's unreal. Friedel-Crafts acylation, alkylation, and electrophilic halogenation. I put chlorination because I spelled it wrong. Because I use chlorine as my halogen. But I want you to look at all these. You start at benzene, you're adding stuff to the ring. See? I want you to notice that all you're doing, see this part here and this part here? See how they're the same exact thing, right? They're all just connected. If you take out the green part, everything is exactly the same, right? You have your iron chloride, right? Trichloride. It acts as a Lewis acid. Over here, here's a picture of it. It has these empty p orbitals here. So the chlorine, even though it's neutral, you know what I mean? They are covalent. They share evenly the electrons. You know, there's it does have a induced spontaneous dipole sometimes. You know, it fluctuates. You know, it's not perfect. Sometimes this chlorine's positive a little bit. Sometimes this one is. You know what I mean? It goes back and forth. That is not enough to do a good reaction, though. That's why you throw in this Lewis base, right? The electrons can come up into this empty orbital, and now you got all these chlorines, 4 electronegative chlorines, grabbing at the electron density. It's going to make this positive, right? By making this positive, now your benzene, it's not negative, but all those double bonds, it has a lot of electron density, right? Now this is positive enough to react with the benzene. You're doing the same thing. Now, if you replace the C with an R, now instead of adding this chlorine, you'll add the R. If you replace this with an acid chloride, an acyl chloride, then the acyl group will add on. It's that simple. But you see how they're all the same exact. I mean, there's subtle differences, you know what I mean? Like this one, you have to use stoichiometric amounts for the catalyst. You know what I mean? You know, little fluctuations in what you do, but it's basically the same exact experiment. But anyways, let's get to this one right here, because this one is what compares to what we're doing. You basically have your product, a benzene ring, put some chlorine in, it reacts with the iron that's in there, and you'll make iron chloride. That will make this adduct, and you'll have this being positive enough to attack the benzene ring, okay? Without the metal, it won't attack the ring. You know what I mean? It might a little slight bit, you know what I mean? You're going to have, if you do this reaction, you're going to have trace amounts, even though there's no metal in there. But if you put metals in, especially a Lewis acid, you're going to attach it to the ring. Now, how do we get it to attach to this benzyl position right here? See, we're starting out with toluene, same thing as benzene, but we got this methyl group. The difference is we use no metal catalyst, right? We use UV light. And UV light, the whole point about UV light is it makes free radicals. It will do a homolytic cleavage of this bond, right? And you'll have 2 free radical chlorines. Now, the great thing about, you know, you can do this to an alkane, like let's say you had hexane. You use free radicals on it, it's just going to pull off all, because free radicals like this, they like to take the hydrogens, okay? They don't like to take them from the benzene, because then that messes up the resonance structure of the ring, you know what I mean? But this hydrogen on here, and it's the only hydrogen that really is good, is the benzyl hydrogen. It's actually the best hydrogen. It's 9 times better than a hydrogen that's on, say, an alkane. All those hydrogens are nothing. This is like 9 times more reactive than those hydrogens, okay? So when you use your UV light, it's going to make the free radical chlorines. And the chlorines, what are they going to attack? They want to attack a hydrogen. They can't take it out of the ring. So what they do is they take one of the benzyl hydrogens, make hydrochloric acid, And now you have a free radical. This would be a free radical, this toluene, right? And what does it do? I mean, the whole place is filled up with chlorine, so it's going to grab a chlorine, right? And then the other part of the chlorine becomes a free radical, and it continues the cycle. It'll grab another hydrogen from another toluene. That toluene will become a free radical, grab a chlorine. Now it's benzyl chloride, but the chlorine that was left, that was stuck to this chlorine is now a free radical. It's just a cycle that goes on and on and on. Now this would be your apparatus, right? This is your dripping in whatever to make your chlorine. I usually use, what do I use? Calcium hypochlorite, because it's cheap and you can get it at the pool place. And I make my chlorine. It would come in here. This would have some kind of drying agent in here, and maybe sulfuric acid or some kind of drying agent. And you would bubble it through the drying agent, and then you would bubble it into your reaction mixture. Your reaction mixture just has the toluene in it, okay? And you're boiling it. You're refluxing that. You can't just do this at room temp. You got to have this, you got your condenser on here. You're refluxing it, boiling it as hard as you can get it. Then you send in your chlorines, not quick, not super fast or whatever, but not slow enough where you are going to have a suck back. You know what I mean? You don't want to suck back. So you have this boiling, you have your chlorine coming in, and then you would have to have either, I'll go into the UV source, but you'd have some kind of UV source putting ultraviolet light on there to do the reaction and make the chlorine into free radicals. And you can see I have a little tube here going into it. This is just an empty container, a suck back, and then I have a container here which would be like sodium hydroxide and water, and that way the HCl that you make would come in here, react with that, and make sodium chloride, and hopefully you wouldn't have any HCl coming out. You should do it in a fume hood though. And that's pretty much the whole reaction. But when you make benzyl chloride, alright, the benzyl chloride is more reactive than the toluene to these free radical chlorines that you're making, right? So once you have so much benzyl chloride, it'll start trying to make benzyl dichloride. You know what I mean? It'll start trying to add 2 chlorines, and it'll try to add 3 chlorines. And I'm going to get into how you can prevent that, or at least keep it down to a minimum. Might not be this video, but maybe the next one. We'll see how long this takes, because I'm not going to try to not edit a lot of stuff. I have an hour video and I edit out 3/4 of it just so I can get it into a 15-minute video. I'm not going to do that with this video. You might say, why is the benzyl position, see, this is your toluene, why is your benzyl position so much more reactive than say a regular, if you had hexane, those hydrogens aren't as reactive as this hydrogen. I want you to look at, let's say this was a free radical, okay, and this is the same if it was a negative charge or whatever. You have resonance. Once this becomes a free radical, this electron can resonate throughout this ring and help distribute electron density, so it's more smooth, more spread out. You know what I mean? And because look, you can jump this over to here, and then your bond comes back. Jump this over to here, your bond comes back. Jump this over to here, and your bond flips back. You have 5 resonance structures, okay? And this charge is distributed throughout these 5 places. 1, 2, 3, 4, 5. It's never put on these positions here, but that's okay. 5 is a lot of resonance structures. So that's why if you take the hydrogen off, that's why I would rather take this hydrogen, because it's so stable, because it can do this resonance throughout the ring and distribute the electron density more evenly. Anyways, let's get into UV sources. All right. Now let's go over UVA, UVB, and UVC first. Those are the three types of UV waves. And here's the nanometers they are: long wave, medium wave, short wave. Right? This is the shortest one. Long waves are like black lights, soft UV. Most of that, if not all of it, makes it through the ozone layer to us. Okay. B, this is the medium wavelength, mostly is absorbed by the sun. Only a little bit of that comes through. And the short wave is completely absorbed by the sun, or by the ozone. It's called hard UV. So my whole point is this: you can use the sun to do this reaction. Just get some mirrors and direct the sun into where the hose is coming out, where the chlorine comes out right here. You know what I mean? And then you'll make your free radicals. You know what I mean? My whole point is, though, this: if you can use the sun, and these are all completely absorbed by the ozone layer, 100 to 280 nanometer, you don't need. You know what I mean? It'd be better, probably, because it's more powerful, but it's unneeded. If you can do it with the sun and you don't get none of that, then you don't need it. This one mostly is absorbed by the ozone layer. I keep saying the sun. This should be absorbed by the ozone layer. But look how it's only like 20 and 15. What's that? 35 nanometer difference between these two. You know what I mean? Like, this is 180 difference. This is, 85 difference. This is just a little bit of whatever. What I'm guessing is that probably the lower the wavelength, the more chance that it has to be absorbed by the ozone. So my guess is that probably about 300 nanometers is what starts getting through the ozone to us. So I would guess 300 to 400 nanometers, that's the highest the wavelength can be. If it's more than that, it's not UV. So I would say between 300 and 400 nanometers is what you need to do this reaction. Like, if you wanted to buy a light that just does UV, you would need a UV light that is between 300 and 400 nanometers, meaning the wavelength. I would guess 300 to 350 nanometer would be the best. I don't know, though. I'm just guessing here. You know what I mean? I mean, yeah, these are facts. I looked up what the UVA and this and that, but I'm just using logic and guessing, basically, here. So like I said, the sun is 300, 400 nanometers, which is good enough to do this reaction. I'm going to either use the sun or I'm going to use a halogen light. A halogen light, and I made a video about this, my UV source will be a halogen light. It produces UV light from 300 to 400 nanometers. The bad thing about it is only a small fraction of the light emitted is actually UV. But I think people have told me that it's good enough. You put the light, you'd have your flask here, and you put your light like right on it. And that way it'll also heat it up, because those things get real hot. And you'd have your heat from it, and you would have your UV from it. Now, if you're going to buy a special UV light that just does UV, keep in mind, just getting 300 to 400 nanometer, that doesn't mean it's going to work, because of a thing called intensity. And I didn't look this up. I don't know if that's the correct word or terminology. But by intensity, I mean, if you have 1 photon per second, because it's a type of UV